Hello everyone, I'm J Wildberger. In this lecture I want to have another look at systems of linear equations, but from some alternate points of view. So we'll be looking at the vector and matrix forms for a system of linear equations. Okay, so a good place to start is with two examples that I showed you last time. The first one was this one right here, involving two equations in two unknowns. X plus 2y equals 2 and 3x minus y equals 3. And we saw that those two equations represented geometrically two lines in the plane, and that their common point of intersection is basically what you get when you solve for x and y. And we did solve, and we got that x and y was equal to 8 over 7 and 3 over 7. And that's that point right there. That's the meat of these two lines. Okay, so that's all well and good. Now today I want to talk about an alternate interpretation of this system of equations. Okay, and this will be a kind of a vector form for interpreting things. So we're going to look at the system as actually being another way of writing the following system. X times the vector 1, 3 plus y times the vector 2 minus 1 equals the vector 2, 3. So can you see what we've done? We've replaced the system of two equations with a single equation, but now an equation involving vectors. So if we look at this equation here, this one, and say look at the top entry of all of the vectors, then we get the first equation in star. And if we look at the second entry, 3x minus y equals 3, then of course we get the second equation. When we write things like this, we can really geometrically get a different picture of what the meaning of this system of equations is. Because we can graph these vectors in the familiar plane, 1, 2, 3, that's x, 1, 2, 3, that's y. Then the first vector is 1, 3. That'll be that one right there. Okay. That's the vector 1, 3. And the vector 2 minus 1. Put a minus 1 down there. So then the vector 2 minus 1 is going down to here. It's that one there. And what about the vector 2, 3? That will be this one here. Okay, that's the vector 2, 3. Okay, so when we solve this system, what we're doing is we're trying to express the vector 2, 3 as a linear combination of the vectors 1, 3, and 2 minus 1. Okay, so this is asking for, we're asking to write a given vector, namely the vector 2, 3, as a linear combination of other vectors, in this case the vector 1, 3 and the vector 2 minus 1. And the answer, well, we know the answer is 8/7 and 3/7, and so we know that actually x equals 8/7 and y equals 3/7 is a solution. And what does that mean geometrically? Well, it means we should take 8/7 of this first vector. Let me go, maybe that's 8/7 of that first vector, and 3/7 of the second vector. That's maybe like that, okay? And then the claim is that the sum of those two vectors is the given vector, and you can see that's working there. All right. So we're taking 8/7 of this vector 1, 3, and we're adding 3/7 of this vector, which is the vector 2 minus 1, and we're getting the vector 2, 3, which is this one here. So it's another interpretation of the meaning of this system of equations. Let's have a look at the same kind of thing with this 3 by 3 example that we looked at. So here we have three equations in three variables, x1, x2, x3. We saw that geometrically we could represent each of those equations by a plane in three-dimensional space, so we really have sort of three planes somehow. Okay, maybe this is not accurate. We have three planes, maybe that's two of them, and there's a third one, and then the meeting point of these three planes will be some point like this. That's somehow the geometry, although that's not an accurate drawing. Okay, now we're looking at another way of thinking about this. So in vector form, this same system can be expressed in the following way. So we're looking at the system here. Let's call it double star, okay? So double star becomes, okay, so the x1 is appearing here, here, and here with coefficients 1, 2, and 1. So we have x1 times 1, 2, 1 plus x2 times, well, x2 occurs with -1 coefficient, 0 coefficient, and -2 coefficient. So -1, 0, -2. And what about x3? x3 appears with coefficients 1, -1, and 2. 1, -1, and 2. And altogether, that should be the right-hand side, which is cumulatively the vector 1, 3, and -2. 1, 3, and -2. So now the interpretation is that what we're trying to do is we're trying to write this vector as a linear combination of these three vectors. We have to choose the coefficients so that the sum of these multiples of these three given vectors is the vector on the right-hand side that we're aiming for. And the answer, well, we know because we've solved it already that x1 is 4, x2 equals 5, and x3 equals 2. Okay. So this works both ways because it also shows us that if we have this kind of problem, okay, that this kind of problem expressing one vector as a linear combination of others really ends up being a system of linear equations. And so it has the same kind of technology employed as when we're finding the meets of planes. Okay, so this is the vector interpretation of a system of equations. Great. Okay, now I want to show you another way of writing or thinking about a system of equations. We'll maybe call this the matrix form. Matrix form for a system of linear equations. Okay, so maybe we'll go back to this first one. Okay, so let's have another look at this thing. And we're going to sort of set up a bookkeeping, okay, bookkeeping to kind of efficiently encode the information in this pair or system of equations. So the ingredients really are of three kinds. The ingredients consist of, well, first of all, a matrix or an array, matrix is just another word for array, of coefficients on the left-hand side. What would that look like? So if we look here on the left-hand side, the coefficients involved are 1, 2, 3, and -1. Right? Those four numbers encode the left-hand side apart from the variables. And we can put them in a little array or call it matrix, and let's give it a name. Let's call it capital A. Okay, so this is what we call a 2 by 2 matrix. 2 means 2 rows and 2 columns. Rows first, columns second. So that's one of the ingredients. The second ingredient is the list or vector of the actual variables that are involved in the system. Okay, so a vector of variables. And what are the variables? The variables are x and y. We're going to organize them in a column, make them into a vector, and then we could give that vector a name. We could call it, say, x, and I'll put a x on top, so that's a vector, okay, the vector x, which is the vector consisting of the two variables x and y. And over here, the third ingredient is the vector of the right-hand side constants, okay, which in this case is 2 and 3. We make a vector out of that, so we could give that vector a name as well. Maybe we'll call it vector b. Okay, so now we have these three ingredients: the matrix A, the vector x, and the vector b. So then we rewrite the equation in matrix form as AX equals B. Okay? AX equals B. AX equals B. That's a general form, or more explicitly as the matrix A, which is the matrix 1, 2, 3, minus 1, followed by the vector x, which is x, y, equals the vector b, which is 2, 3. Now, what we're really doing here is introducing some new kinds of mathematical objects. We're introducing the ideas of matrices and vectors, and implicit on the left-hand side is an idea of multiplication. Okay? So to actually really make sense of this, we have to define what we mean by the product of this 2x2 matrix and this vector. So let's do that, and so let's introduce matrix multiplication, which is a very important topic in linear algebra, and it's making its appearance here. Matrix multiplication with a vector. It's a special kind of matrix multiplication. We're going to be looking at more general products later, but this is sort of the baby case. Okay, so the first definition is to multiply a row vector by a column vector. And it's important that they have to be of the same size. Okay, so they have to be of the same size. So I'll do the 2x2 case first. So suppose that we have a vector, let's say v1, v2, and we have another vector w1, w2. So the first one is a row vector, and the second one is a column vector. Then we're going to define their product, v1, v2 times w1, w2, to be the 1x1 vector, v1 times w1 plus v2 times w2. That's a definition of how you multiply a row vector by a column vector. More generally, if we have vectors with n components, say v1, v2, all the way up to vn, then we're allowed to multiply that by a column vector of the same size. Say a vector w1, w2, down to wn. And the definition of that product is, again, a 1x1 vector, which is the sum of v1 times w1 plus v2 times w2, all the way up to vn times wn. That's how we multiply a row vector by a column vector. Okay, so for example, if we have the vector 1, 2, 3, and we want to multiply by -1, 5, 4, well, this is going to be 1 times -1 plus 2 times 5, we don't need that bracket, 2 times 5 plus 3 times 4, which is a grand total of minus 1 plus 10 is 9 plus 12 is 21. And so we'll put it in a bracket. Now, you've seen this before, okay, because this is really just the same as the dot product of the two vectors, with a slight difference in that the two vectors are not both column vectors. Now one of them is a row vector and the other one's a column vector, but it's really just the same as a dot product of vectors, okay? So this is just another form of the dot product of two vectors. Okay, great. And now we are in a position to extend our definition to defining the product of a matrix by a vector. Okay. So before I do that, I have to tell you about the sizes of matrices. The sizes of matrices. So a general matrix, not just a small one, but a general one, we often write it in this kind of form here. So maybe the entry up at the top is A11, and then the next entry will be A12, and then A13, all the way up to maybe A1n. Okay, well that means that there are going to be n columns. Okay, that's the first row of this matrix. In the second row, we're going to label the entries A21, A22, up to A2n. That's the second row. And then down to the last row, which we'll say is the mth row. Okay, so it'll start with AM1 and then AM2 all the way up to AMN. All right, so have a look at this. This is a kind of a general nomenclature. We're organizing the elements in an array. So when we say Aij, this means the entry in the ith row and jth column. So for example, this thing here, okay, that's AM2. That means that we are in the mth row, and in the second column. Okay, the M tells us which row we're in. The 2 represents which column we're in. Okay, so that's how the indices work. The first indice is telling you which row you're in, how far down you have to go. The second entry is telling you in which column you are, in other words, how far right you have to go. Okay, and this kind of matrix, this matrix has a size. The size of this matrix it's an m by n. Okay, it's m by n. So sometimes we say MMN stands for the matrices of size, matrices of this size m by n. Okay, great. So now I can tell you how to multiply a matrix by a vector. Okay, I'm going to do that with an example first. So the product of a matrix with a vector. Okay, but there's a condition that has to be satisfied. If the number of columns of the matrix equals the number of entries of the vector. So let's do an example. So let's say we have, here's 1, 3, 2, minus 1, 4, 5. Okay, this is a 2 by 3 matrix. It's a 2 by 3 matrix. It has 2 rows. It has 3 columns. We are going to multiply it by a vector whose number of entries is the same as the number of columns. Maybe 2 minus 3, 1. 2 minus 3, 1. Now, how are we going to define this product? Well, what we're going to be doing is we're going to be looking back at what we've defined already, this product of vectors with vectors. Where's the product of vectors with vectors? Right here. This product of vectors with vectors, or maybe this is the more general one. Okay. So we know how to multiply a row vector by a column vector. What we're going to be doing is we're going to be applying this same formula as many times as we can. As many times as we can. So let's go back to here. So we want to look for row vectors that we can multiply by column vectors. So here is a row vector. Here's a column vector. So we're going to multiply these two together. What do we get? So we get 1 times 2 plus 3 times minus 3 plus 2 times 1. And that's going to be the first entry of our product. The second entry of our product is going to be what we get when we take the second, I might do it in a different color, the second row and multiply it by, well, there's actually only one column on the right-hand side that we can multiply, the same one, okay? And when we do that, we're going to get minus 1 times 2 plus 4 times minus 3 plus 5 times 1. Okay, and so that is a grand total of, let's see, 1 times 2, that's 2, plus minus 9, that's minus 7, plus 2, that will be minus 5. And the second entry is minus 1 times 2, that's minus 2, and then plus minus 12, that's minus 14, plus 5 will be minus 9. Okay, so that's what we get. We started with this 2 by 3 matrix. This vector, well, it's also a matrix. It really has 3 rows and 1 column, so we could say that it's a 3 by 1 matrix. Okay. And then the result over here is something with 2 rows and 1 column, so that's a 2 by 1. So this is how we multiply a matrix by a vector. Okay, so let's now go back to finish off. Let's go back to that other example that I had where we had a system of 3 equations in 3 unknowns. Okay, so let's have a look at this example where that was one of the things that we were already looking at today. I think we called it double star. Let's have another look at it now from this matrix point of view. Okay, so the 3 ingredients here are the matrix of coefficients. So A is the matrix of coefficients, and they are 1, minus 1, and 1. The coefficients of x1, x2, and x3 in the first row on the left-hand side. And then the second row, 2, 0, minus 1, because there's 0 x2s in that second row. And then 1, minus 2, 2, that represents the left-hand side of the third row. Okay. So that matrix, that's a 3 by 3 matrix, that encodes or captures all of the coefficients on the left-hand side of the equation. Then the other ingredient, the next ingredient, is the vector of variables. There are 3 variables, x1, x2, x3, so we make a vector out of them. Okay, a matrix kind of includes the notion of a vector. A vector is a sort of special kind of matrix. You can see a vector is a special kind of array where there's only one column. So as a matrix, this would be a 3 by 1 matrix. And the other ingredient is what's on the right-hand side. Let's call that B. That's the vector 1, 3, minus 2. So now we want to rewrite the original system as an expression or an equation involving these three objects. Okay, so we're going to write star now as the equation AX equals B. That's the short form involving these short forms. 1 minus 1, 1, then 2, 0, minus 1, 1 minus 2, 2. The vector x is x1, x2, x3. And the right-hand side is the vector b, which is the vector 1, 3, minus 2. Now I want to convince you that this is consistent with the way we described the product of a matrix by a vector. So here is a matrix, it's a 3 by 3 matrix, and here is a vector, it's a 3 by 1 vector. Let's just make sure that we appreciate what the product of these two things is. Okay, so let's rewrite this left-hand side by actually writing out this product of this matrix times the vector. Okay, so what are we going to get? So what we have to do is, I want you to think about, there's rows here, okay, there's 3 rows here, and there's in fact only 1 column here, okay? And what we're going to be doing is we're going to be multiplying rows times columns, rows times column, rows times columns, rows times columns, okay? We're going to do all possible products of rows times columns. That's how we multiply this matrix with this vector. Okay, so what are we going to get? So the first row times the vector will be 1 times x1 minus 1 times x2, so we have to add that, so it's minus x2, plus 1 times x3, so that's plus x3. That's the result of the multiplication of the matrix by the vector. The second entry is the second row times the same column on the right-hand side. So it's 2x1 plus 0x2 minus x3. And then the third product is the product of this third row, 1 minus 2, 2, with the same column vector. That's x1 minus 2x2 plus 2x3. So that's the result of the left-hand side, and that's equal to 1, 3, minus 2. And we see that that is indeed just kind of a vector form for the system up here, system double star. It's just another way of writing it where we've written all 3 equations basically in vector form. So this is really the vector form that we talked about earlier for that same system. Another way of writing the vector form. Okay, great. So we have introduced the matrix of coefficients. We've introduced that's the vector matrix of coefficients. We've introduced the vector of variables, and we've introduced this vector of constants on the right-hand side. There's one more kind of way of encoding everything, which is called the augmented matrix. I'll mention it here just to finish. Augmented matrix of this system. If we're just interested in sort of, getting our computer to remember all the numbers that are involved, what we can do is we can take the matrix A, which is right here, and the right-hand side, those are all the numbers, and we can kind of put them together so that they're all together. That's called the augmented matrix. So that will be, maybe I can squeeze it over here. So 1 minus 1, 1, 2, 0, minus 1, 1 minus 2, 2, and then we put a bar across to separate from the right-hand side, which is just this matrix of constants on the other side. So another way of saying that is we're taking the matrix of coefficients, which we are calling capital A, and the vector of constants, which we're calling B, and we're putting them together, sort of augmenting the matrix A with another column, and we're calling that the augmented matrix of the system. And that's really all that we need to actually perform the main technology of row reduction or Gaussian elimination, which is the technology that we're going to develop for systematically solving bigger systems of equations set up in this sort of matrix fashion. So see you then.